All right, so first up, Vinesh Sukumar.
That's good.
I butchered it. I apologize, but yeah. Okay, so he's the Senior Director and Head of AI ML Product Management at Qualcomm. Vinesh has worked at NASA, Apple, Intel, and a variety of other companies. 20 years of experience spread across research, architecture, engineering, and application deployment. Then we have Prashanta Saha, AI ML engineer from Google. Has a PhD in computer engineering from George Washington University, and currently working on advancing neural architecture search and large language models through the use of AI accelerators. And you spent 2 decades at IBM prior to this, and George Washington University. And then finally, we have Bhutant Sartsmurray. Sartsmurray, okay. Didn't write your name out here, so I have to read it from there. Or there. So VP of Technology, Business Development Partnerships at Brain Corp. Has been there for the better part of the last 5 years. And your role is obviously to lead business development and partnerships, and you're responsible for assessing and determining relationships instrumental to Brain's growth and technology roadmap. So I'm going to ask each of you to give your opening remarks, starting with you, Vinesh, and then we'll get into an open conversation.
Yeah, sure. Thank you for the opportunity. Thank you for the generous introduction. So at Qualcomm, it's all about edge deployment for us. And one of the biggest questions we try to answer is how can we accelerate solution deployment? We deploy approximately about 200 to 300 different applications and use cases from convolutions all the way to generative models. So it's quite important that we put emphasis on getting that enabled. And second thing is how can we really push for enabling common sense in AI or more towards cognitive AI, right? So that would be my opening statement and how Qualcomm is actually pushing for it.
Awesome. Hey, everyone. So I am part of the Cloud AI team. And as you know, Google has been in this space for quite a while. There's a lot of research that's happening at Google. And what my team does is enable you to be able to do some of these things. And one thing that we've seen recurring is that it's very, very difficult to try to optimize between multiple different sensors, as we saw before, multiple different cameras, multiple different chips, software, and make it all work, concurrently, if you or together. It's one of those challenging problems, and that's one of the reasons why we developed neural architecture search early on, so that we're able to fine-tune specific to your camera, specific to your chip, specific to your product and software, so that you can get that accuracy and latency without sacrificing a lot of the behaviors that you're expecting. So a lot of times you're developing these chips on your desktops and developing the software to go with it, and you end up seeing that the state-of-the-art model that you grab from some of the latest research paper works nicely on your desktop, but all of a sudden when you push it to the edge, they don't work as well. Right? There's a number of things that you need to tune, and when you tune one, you break something else, and you tune the other, you suffer in somewhere else. And so that's why we've sort of built a number of tools to allow developers out there to get the best out of their specific hardware, their specific sensors, and their specific software. So that's what I'm going to be talking about today.
Fantastic.
Hey, Bhutan Satmar, I've been with Brain, not from 5, but from probably like 13 years when we started the company. And Brain Corp, you may not guess from the name, it's a robotics company. To our surprise, BrainCorp.com was available, so we quickly grabbed it. And we are happy beneficiary of all this amazing technology that Prashanta and the Google team is or has been developing. So, as I said, we are a robotics company. One of the primary product that we are doing is navigation. So, we don't build our robots. We develop navigation technology, just like Waymo does. Maybe everybody understands that model. Waymo is not building cars, but it's turning them into self-driving cars. That's pretty much what we are doing. So we have a variety of platforms, from the seemingly boring or maybe boring cleaning robots to delivery robots and all sorts of applications that's like it almost doesn't matter for us. It just needs to navigate indoors. We have about close to 20,000 robots out there. You may not see them because there are many, although they operate in public spaces, but often at times when we are sleeping or behind the scene. And we talked a little bit about like how do we use AI and what's deterministic. So we really go from edge to edge. Some of the safety part for us has to be deterministic, and we go all the way to the end when we use AI to deliver some complex functions and maybe based on visual understanding of the scene, change the behavior of the robot, or determine what's on the shelf in a retail environment, and based on that, provide some analytics back to the retailer.
Fantastic. So your ODD really just hides it from people's view mostly, right?
Sorry, say this again?
Your ODD just hides it from people, so people don't see your robots when they're out and operating.
No, it's not that we hide them. They are pretty big sometimes. They just operate, say, at 3 a.m. in the morning.
Right. So we're going to have to go find them, right?
Yeah.
All
Or
right,
if your
thanks.
flight is late, you may see them at the airport.
And be gentle
I
when
hope
you see
not.
them.
I hope not. All right. Yeah, no, thanks for the intro. I think we've got most of the people back as well. So let me start with this, right? So you've got computer vision and you've got neural architecture search. What's the intersection? Any of you? What's the relation? How it enables each other, and you can also go into the challenges. So.
I'll start. And obviously, I mean, by the way, so I'm very, very privileged to be in this panel. It's like there's a collective number of decades amongst us with this experience, and so happy to answer some of these questions. So, vision is one problem that has been hard to solve with just intuition, right? So when you've seen a lot of really, really good, spectacularly good software that's able to do AutoML on tabular data and things like that, you can sort of see some of the capabilities built because based on intuition, right? Maybe you do some feature crosses here, you do some interesting data handling there, but vision has been very, very difficult. It's been sort of like, once you tried the state-of-the-art model, where do you go to next, right? It's not that you can just randomly add another layer and then sort of intuitively figure out what to do next. This has always been sort of in the forefront as the next state of the art will then make my software 2x better. And so because of that, we've seen a lot of delays in people's product pipelines and things like that. It's just not feasible to do it with intuition alone. So this is where neural architecture search really comes in. So beyond just doing hyperparameter tuning, which is black box tuning outside, how can we go inside and look at your model and say, well, if you move these layers around, this is what it's going to look like. If you do the skip layers, this is how much more efficient we'll get. Hey, you really need to fit into a robot that has a finite amount of battery power, right? So how do you optimize for one model so that the battery power is also optimized for? So now you're looking at accuracy, you're looking at latency, you're looking at the memory, you're looking at the processor power, you're looking at the various different levels in your sensors and things like that. It's a very difficult, hard problem to solve. And this is where neural architecture search kind of helps you, right? It's going to take one point and sort of compete it using your reward function, find the best solution that you can offer for that specific solution. So this is exactly where autonomous driving, for example, has been a very big user in this space. So the AV customers, for example, they need to optimize for LiDAR. They need to optimize for their camera sensors. They need to optimize for radar. They need to optimize for the memory and the battery and everything. And this is where combining all those together and finding a solution that fits your specific window of latency and accuracy is very, very difficult to do by hand. That's where neural architecture search really comes in. So I know it seems like a long-winded example, but essentially, the reason why vision started first was because it was just really hard to just solve with just intuition. You cannot just apply intuition and sort of get the next state of the art. You're going to have to evaluate a lot of these hard problems like, sensors and memory and battery in order to get there.
Yeah, maybe to what Prashant had added is one of the biggest challenges we face at Qualcomm, I would say, is scalability for solutions. When you look at scalability of solutions, what does it actually mean? If you're looking at, let's say, a mobile device, you have a price point of a mobile device that could go from a $100 price point to a $1,000 price point, which basically translates into a different compute profile. And as such, when you happen to have vision algorithms that could be segmentation, detection, recognition, whatever class of a DL architecture it is within the vision umbrella, it's very different. Now, you're not going to have infinite number of resources to be in a position to optimize a model for every given compute footprint profile of a mobile device, right? And it's the same thing even for an automotive space. We look at the levels of autonomy from L2 to L5 as such. You're going to have elements of drive policy or perception stack that you want to really enable. But the physical access to the number of sensors or the configuration of the sensor file itself, in other words, it could be a 2 megapixel or 5 megapixel, the field of view, whatever that might be the definition, is very different. Now, when you happen to have plethora of options on the table and you have to launch these applications within a very defined time frame, obviously the common human intuition would be is let's put a ton of software engineers on this, let's start optimizing every single layer, every single op to really make sure it fits the profile, right? That's historically been the tradition, and I'm pretty sure it also continues in many areas and forums. But really expedite that, neural architecture search really helps, because you can actually use AI to optimize AI, right? That's the end of the goal. And how do you really do it? It's really bake in these hardware intrinsics. These hardware intrinsics could be configurations of memory profile, configurations of latency, configurations of quality of service, and many other elements that actually define what a key performance indicator or a key experience indicator is, and then absolutely solve it. And I think the earlier question, why vision? To a large extent, either good or bad, vision happened to be the most commonly used use case and the most complex in many areas. I'm not suggesting linguistics recommendations are not complex. We're getting there, but it starts off with vision, then obviously migrate to other domains.
Any thoughts?
Yeah. So as I said, we are direct and indirect beneficiary of all this good stuff. To give you an example, like 20 years ago, I was working on a license plate recognition problem for like a parking house in Japan, and like the problem that I had to solve was down to a pixel level. It's like, what am I doing in this case and that case? Like, we are so far from there. Like, I can work with Prashant and other teams within Google or others and say, hey, I want to recognize products that I'm seeing on the shelf, and look, I'm almost getting that solution out of the box. It's amazing. It just works. It's almost boring. There's a lot of work behind it, but boring is good. It's like in a couple of years, we will see self-driving cars, and it won't be exciting, and that's a good thing. They will be just driving on the street. No one will care about them if we get there or when we get there.
Boring is good if you meet your con ops, right?
Say it again?
Boring is good if you meet your con ops.
Yeah. So we are a beneficiary of it, that it works to the level of almost boring, which is an amazing thing if you think about it. It's the challenges that we have, for example, for say product recognition. A robot runs up and down an aisle, it needs to see what's on display, and based on that maybe provide some feedback to a retailer that what's available, what's not available, what needs to be restocked, and all these kind of things. If you go to a large, if you take a retail store, it can have, say, from 3 to 150,000 unique SKUs. You're showing an image, it has to tell you what's on the image. it's an amazing, it's a very complex and difficult thing, and this level of problem is like, through the benefit of all these amazing learning algorithms and whatever, it is almost come out of like as a canned solution.
So let me pivot to this and ask this, right? So we're talking about scale. So one thing that you obviously mentioned is the neural architecture search, which gives you the ability to not just use intuition, but actually try to optimize at layer level. How does that translate into scaling? Because, and I'm just playing devil's advocate here, this sounds to me more going further deeper down and making it even a more burdensome problem to scale. So how do you address that, and to all of you, what is going to enable this? How, to build it at scale? And when you say boring, you have gotten to the right scale. So, you start with maybe 1 robot, then you go to 10 robots, then you have to go to 100, then 1,000. And those are big steps, right? So maybe also paint a picture for our audience. What are those big discrete points that fundamentally change your infrastructure or your framework to enable that scale?
Actually, you want to go first?
Yeah, great question, I think. Scale obviously could be defined in many ways, right? One element I'll probably anchor on is experience scaling for a user. What that actually means is, again, as a smartphone user, my expectation is if I happen to have some kind of image enhancements, can I get that image enhancement experience scale from a $1,000 platform to a $100 platform? Right now, that is a difficult problem to solve because you often end up not being in a position to provide the same user experience. How can that be accomplished? Right, so that is one problem. The second element of it is, can I do this experience scale year over year without making sure there is not much of a compromise on the application portability? How is that going to work? What do I mean by application portability? Maybe I should emphasize that. When you look at many independent software vendors, let's take Adobe, Cyberlink, any popular vendor, right? They would like to work with multiple platforms, whether it be x86, ARM-based, Apple, Qualcomm, whatever that might be the case. For them, they need application scale, meaning at any given point of time, they need to be in a position to seamlessly support that experience across multiple platforms. For them, that scalability is important. And how do we really provide that infrastructure to really support application scalability, right? So, you can answer this in many ways. But at the end of the day, the question is, are you able to support the developer? Are you able to support the ODM vendor? Are you able to support the platform enabler? Are you even able to support the OS vendor? And that scale, for good or bad reason, always touches the hardware and the software layers supporting the hardware. Because if we don't do that, the scale that we're talking about is a function of price point, is a function of hardware, just doesn't happen.
So I could take the scale in terms of the benefits that we get after NAS is the next state-of-the-art model that comes out. It's someone's going to publish it and say, hey, listen, if we put these layer in this sequence, you're going to get a much better product, right? Your vision model is going to be so much better, but it takes that initial drive to put it into perspective, run it for thousands of hours, if you will, and then get that highly accurate and highly tuned model for, let's say, a specific car model with a specific LiDAR, with a specific battery size, with a specific camera sensor and radar, for example. And then you can then publish that. And as Google has published a number of these neural architecture search papers, where people can then use those to scale models outside of the use case that Google has, for example. So, and as Bhutan was mentioning, we actually put some of these into our AutoML and Vision AI platforms. So now you're getting the benefit of these thousands of hours of runs to be able to now, out of the box, get a highly tuned model that has learned from these previous runs, if you will.
Okay.
Yeah, scale for us is and probably not just for us, it's mostly an infrastructure problem.
Yeah.
Like when you take just the core function robotics, I mean, it's very different when you have one robot out there, you said, versus even 500.
Right.
And then it's very different when you have like 10,000. So you have to have really have the proper organization, and then that supports this. So you need to make sure that they work from here to San Diego and anywhere in between and beyond. But the good thing is that the core technology that supports this infrastructure is there. So to give an example on, like, say you want the robot to perform any, like, in the context of this conversation, some vision-related task. The infrastructure is there to sample enough data that represents a good enough variation. And once you have a good enough sample, the learning algorithms and the corresponding vision algorithms are there. You can train them almost easily so that they work in a variety of examples. So if you have the infrastructure to collect the data, then the infrastructure and the technology to train your models and train your AI is there to support things at scale.
Okay. I'm going to come back to scale later in this chat. So maybe let's go over to our participants and see if anyone would like to. All right. Is there a? I'll steal your mic.
Can you hear me? Okay. So yeah, my name is Shakti, and I'm a software engineer at Zoox. So when you talk about NAS, what are the typical training costs associated with them? For example, I believe you mentioned you work on NAS for like large language models, and as we all know, like those already require like thousands of GPUs. Adding NAS on top of that, how does that affect that? A second part question would be, even though NAS has been around for a while, we see a lot of state-of-the-art from hand-tuned models, for example, BERT, GPT-3, or even in vision, like vision transformers. So why haven't we seen NAS doing state-of-the-art stuff?
Yeah, so NAS is being used quite a bit more. So I'll give you an example from our latest release of the Pixel phones, for example. Hand tuning models only get you so far. So in order for us to move, being able to detect voice on the phone from taking a round trip to a cloud, for example, we were able to optimize it such that it now fits on the phone itself. So that's an example where it would not have been possible if we were going to hand tune this, because it's just, the model would be too big to fit on the phone. So that's one example. Another example from the same phone, if you look at the amount of battery power that it uses to what we call face blur, right? So to be able to take a blurry image and then sort of sharpen that image, it takes a lot of compute power. And the team that was developing that specific software was able to use NAS to sort of not only get better accuracy, but 30% less energy, right? So there's a number of these things that are yes, you're right, there's always going to be some more hand-tuned models that are going to come out. But from us, from our perspective, from about 2017 forward, we found that NAS was steadily able to, not hit the plateau, if you will, steadily increase the accuracy and get better at it. So we've seen a number of models that are coming out of Google that are really based out of neural architecture work. And you'll see a lot of them, actually being published and available for reading as well. But you're right, there are still going to be folks that are going to be, hand tuning it because maybe there's some intuition or experience that can help there. But NAS we've seen steadily improve the model size, the model accuracy, energy consumption, and things like that. So I hope that answers your question.
Yeah. And what about the training costs associated with NAS?
That's a good point. So because NAS is based on a reinforcement learning model, there is no getting around starting from scratch, right? And it's going to do randomized, testing until it gets there, right? So you can control costs based on how you see your model tuning, right? So the reward function is really what controls the cost, right? If you put in an extremely stringent reward function, you will be running it for a very long time. But if you have, let's say, hey, I want to go from 5 millisecond detection of cars, right, to 4 millisecond detection of cars, that's more reasonable. For example, you can sort of stop at a much earlier cost, but the cost is basically associated with the GPU runtime.
Thanks.
Okay. Next. I promise you there's a break in 10 minutes. All right, I feel like you're getting into peer pressure, but go ahead.
So just to follow on from what we just discussed, do you see a world where NAS sort
Sorry, can you introduce yourself first?
Sure. My name is Abhishek. I work at a startup called Coldpress AI. So just to follow on from what we just discussed, do you see a world where NAS sort of, I wouldn't call it obliterates, but it completely becomes the norm and the standard in the foreseeable future?
Yeah, it really depends upon what problem statement you're really trying to solve, right? I think there was an earlier question in today's discussion is, especially in the autonomous space, we have different flavors of sensors. And are we going into, let's call it, a foundational model that really supports different classes of these sensors rather than having an algorithm for every sensor, right? Obviously, NAS has one good infrastructure support for that. Can we really get into that model of enablement? Because if you compare that to a human investment to really look at models based on thermal sensors or LiDARs or radars, that's about 6 to 9 months of research only. Now, yes, would that be an added server infrastructure cost? Absolutely. But my personal belief is you can get to a faster unification of a foundational model to support these different classes of use cases because you know exactly what KPIs you're looking for within a month compared to that. But again, it's a very specific problem you're looking at and then getting it done. Now, there could be commodity-based use cases. Commodity-based use cases could be, let's say, person detection, face recognition, those kind of stuff. Those are very well established in the industry, has been in this industry for quite some time. The question really becomes as, really you want to spend server infrastructure costs to optimize it, I don't know, from 78% accuracy to maybe 80% accuracy? Not really, right? So from that perspective, I don't think NAS is really going to help unless somebody comes back and say, okay, fine, I really want this facial recognition, but it needs to fit a compute profile of 100 GOPS. Then we have a problem, right? Maybe at that point of time, you can start looking at NAS to really get there. But from my experience, it is mostly tailored towards very specific problem areas. Then you go towards areas we really want to drive scale, and then commodity not at this point of time would be my expectation.
Fair enough. Thank you.
Botun, do you want to add anything to it? Like, are you planning to, are you using, if you're able to share, NAS as a standard implementation for your robots?
Mostly not. So it's so the vision problems that we need to solve is so they are. So I'm going to repeat myself. So we are the beneficiary of the work that has already been done that use NAS, etc. So to optimize models and find what works best. So for us, it's already a solution.
It's a tool set. It's a tool set for you that you're going to apply.
Exactly,
Okay.
exactly.
So that's
That's a great thing. Yeah. So it's like, okay, it's almost like the fact that I don't have much to add is a really great thing because it's matured to the point that I'm just a happy user of it.
Yeah. So then let me ask you, is it mature enough that, let's say, someone wants to do a robotic startup today, can they actually use those tool sets and build right off the bat using NAS?
Yeah, so NAS has traditionally been sort of like a tool of last resort, where you've already fine-tuned your model, it's really not getting there. You're not going to get regulatory approval until you get 5 millisecond latency for your car or something like that. That's when you start looking at NAS. A lot of the beneficiaries, for example, we traditionally move the models that we find from NAS and then move it further down the chain, for example. So from the AutoML perspective, from the Vision AI perspective, they're all using NAS models today, right? So you get the state of the art, everyone benefits, right? But where NAS really pays off is when you have a model that needs to meet a specific criteria, right? And for example, the Boston Dynamics team, right? There's a battery involved, right? Yes, we can figure everything else out, right? But we don't know that our model is negatively impacting the battery. How do I make sure that the battery is taken into account as it's developing the model, right? So that's where it starts becoming to play, right? It's not something that you use off the bat. But yes, if you already have a very mature model that you need to further improve, that's where NAS really comes in handy.
And maybe to add to it, it really changes and enables a different type of engineer to work on these problems. So say 10 years ago or whatever plus, you had to come out of, I don't know, as a postdoc from Jeff Hinton's lab to be able to work, even just understand what you are doing.
Right.
And now we're talking about a cloud engineer maybe with not much of an ML background or computer vision, et cetera, background is able, because of the availability of these tools and technology, is able to work on it and solve amazing problems.
Yeah, I mean, it's getting reduced to practice, right?
Exactly.
Turns into tool sets that you use. I think the point of establishing that question was that this is not your first step. NAS is your fine last mile, so to speak, because you're essentially optimizing the architecture that you've already built,
Yep.
right? So as further developments would actually put it more reduced it to practice so that you can actually implement it for a broader use cases, I suppose, right?
Yeah, I want to just reiterate that NAS is not sort of like this magic tool that you just plug in your model and it'll just spit out something. It is still going to require you to put in the effort to say, I want to try these specific things, but I don't know intuitively if they're going to make sense, right? So you're gonna basically tell NAS to sort of say, hey, these are the kernels that I want to try, like an NVConf or an conf or something like that. And oh, by the ways, these are the skip levels I wanted you to try. And oh, by the ways, I wanted you to try this, this, and this. It's sort of like taking what you would normally do in the span of 1 year and just assigning it to it. It's like, it would take me a year to do this. NAS, can you take this and provide me the best combination of my search space? So it is still depending on that.
Yeah, I mean, in history of optimization, right? There's never been a tool that you just give it to it and let it run it, right? You got to define your problem.
Yep.
And that's what I tell everyone that I work with is like, what I care about is how you set up the problem. I don't really care about how you're going to solve it at the moment, right? So we have time for one more questions, and then we'll go into closing remarks. That gentleman was first, so we'll see if there's time I can come back or afterwards.
Yeah, hi, I work for Boston Dynamics, and my name is Ho Jun Ji as a perception engineer. So it sounds great, like the NAS and all the scalable intelligence system, but like, what are the challenges you think that needs to be solved to make it really widespread use, like for, as mentioned, but for a startup to be able to use it? I think there are some responsibility from the client side as well to collect the data in certain format, and like how do you, like, what's the challenge to solve in that to make this more widespread usage kind of like scheme?
Yeah, great question. I think, let me simplify probably the answer. I think from a technical acumen standpoint, you need to have some level of comfortness on understanding your architectures, right? So I would suggest it's not for any common ML engineer. He needs to know exactly what he's trying to do, right? So you need to have some flavor of technical acumen. So that's one portion. The second portion of it is, you use NAS basically to modify the structure of a head or a backbone of any given, let's say, a task. But that's happening on the cloud, right? And it gives you a few recommendations. The expectation is you need to have the hardware intrinsics in the loop, wherein it physically tests it on the device to actually make sure that the head and the backbone actually make sense. So the connectivity from the cloud to the edge needs to be established. Now you could do that in two ways. One, you could, have your inference software stack get mapped onto Google to make sure that you have that connection set up. or you could physically emulate your entire platform and put this on the cloud, right? Which is a difficult problem, but yes, it can be doable. So that would be, one element of it. And the third option of it is, obviously you need to have access to the right set of data, right? Because when you try to modify or tinker around with these models, it always maps back to the data sets. You can't generally apply whatever data set you want. You really want to make sure what problem statement you're trying to solve. If it is synthetic data or original data, can I do a combination of synthetic and original data? And they have to be structured, annotated, and filtered in a very clean way that when you do these mapping, it kind of gives you the results. So what I'm going to suggest is the infrastructure establishment needs to be clean enough to really make sure all these three work, right, to answer your question.
Okay. All right, so we are over time, so closing remarks, about 30 seconds. I'm going to ask something specific from all three of you. So, Botund, if you can talk about, as part of your closing remarks, what would you tell an aspiring startup in robotics who wish to scale to 1,000+ robots at some point? What is one advice you will give? Prashant, you should tell us what is the next big thing, whether in NAS or beyond NAS. And Vinesh, can you comment something about hardware? Because you did bring that up, especially on the cost optimization side. So please, you go first.
Didn't have time to think about it, but yeah, what I would advise is make sure you solve a problem that makes a business sense and doesn't just look cool, and you put your effort into differentiating things. So, like having a robot that navigates around just for the sake of navigating around, there is a million of those by now. So if there is an off-the-shelf solution for something, go out and use it and focus on this very specific application that you are actually want to solve. That is a business differentiator for you. I see with robotic companies often that they solve problems that many others have already done, and it won't make them any different than the rest.
So business case, know what your business case is, what are your user stories, right? And I would not expect anything less from you, being that you're in business development side. But yeah, thank you very much. All right.
So the question was, what's coming next, and sort of what advice would you provide to startups? I think the first
Sorry,
thing.
feel free to make predictions, like wild predictions. Go for it.
No. I will get my badge taken away if I do make predictions here.
It's a safe space.
Yeah, no, I think the primary concern that we've seen a lot in this space is cost, particularly training costs. It's something that people have been trying to solve for a while, particularly even with NAS, right? Being able to find something that is able to get like these 5 different objective functions and correlated. And by the way, some of these objective functions are completely orthogonal, right? You optimize something and all of a sudden the other side of the equation doesn't work, right? So this is where compute power really helps. And so at Google, we're continually investing in multiple different types of accelerators, and you may have heard some of them as, TPUs, the tensor processing units. So we're creating new generations of those to reduce the training cost even more. And hopefully, that's at some point, we're going to get to a point where this is just going to be commonplace, and you should be able to train some of these rather quickly. But in terms of advice for startups, it's just, as Botund was mentioning, right? This is something that we've seen over and over again where because you don't have the data, you're grabbing it from open source and you expect that same data that's coming from open source to work on your specific vehicle, for example, or specific robot. It doesn't always work that way, and that's one of the reasons why having that rich set of data is very, very critical. If you have it, I worked with a customer recently where even the camera angle matters, right? Where you mount it. And so, having the right data would seriously cut down on the amount of time you need to get to your final model. Because training on general data is great. I mean, you can do transfer learning, you can do all kinds of interesting things, but if you want it to be specifically work for your model, having that data is very, very important.
All right, thank you. Vinesh?
Yeah, so I think the closing remark on hardware, or specifically on scale. I think I'll probably answer it differently. Moving forward, the expectation as a function of an ecosystem is, can you really drive towards inference personalization? Wherein you can actually position your inference to be more closer to what the user wants. And it's very different from a user A to a user B. So what kind of architectural investments can be really done to really supplement and support that? That will be one portion of it. And the second portion of it is, inference personalization could be, enabled within the device, especially when you happen to have confidential data. Another one is when you happen to work with many automotive customers, can you really take the car to cloud as a service infrastructure, and then can you take some level of unsupervision to really customize that behavioral pattern or drive policy specific to that driver. So a lot of focus and emphasis on that portion. Now, I'm not suggesting by any means, compute features like sparsity, data types, memory to compute ratios, bandwidth optimizations. Those will always continue, right? You're never going to put a stop to that. But those are basic foundational blocks. So my expectation would be, what do you do beyond that to really impact the user using AI, and how does really hardware provide the infrastructure to really support that?
All right. Well, thank you very much. Appreciate everyone's participation. We're going to have a break, but let's give our guests a big hand for their.